All right, gang, can you hear me out there? Anybody hear me? Yeah, you can. Might be virtual, folks. Sometimes the mic isn't set up right. You're not saying anything. Yes, but we got to type in yes. I like that. All right, great. Weather's going south, guys. It's raining out there now here in our neck of the woods. Still warm temperatures out there. Drive safe and still enjoy the good weather. All right. So today, the last regular Wednesday class, better known as Veterans Day, November 11th, 2020. It's 8 AM class, page 1. All right, so remember, this is our how it's all going down so far. November, I guess I should say, let's see, hold it, November, heck with that. November 12th. Thursday, AKA tomorrow. Final homework is due. Homework number 10, due by 6 p.m. And then we got to get through Friday the 13th on Friday, obviously. And then next Monday's our last regular scheduled class. And then we do November 18th. Next Wednesday is exam number 3, or whatever we cover up to Monday, which is going to be momentum. November 20th, Friday. That's makeup exams. If you don't have a makeup exam, you need not worry about anything. But we don't know that until you get through Wednesday. And finally, 21, November 23rd, Monday, from 9 a.m. to 10:50 a.m. Final exam. Luck on that. That's it. The only thing not up there on the date wise is the Friday class and the Monday class. We're just clicking them off, guys. Almost there. All right, so where are we at? We're talking about energy. And I guess I can review a little bit. Last time, we struggled to get to the work done by the gravitational force, and we connected that into a term called energy, potential energy. So UG equals gravitational potential energy and that was defined, I guess it's we don't really do anything with that, but what we like to do is we like to work with delta UG. We want to know a change in it because that's going to, well, it could rob you of energy, but it also could be stored energy then. You raise an object up high, like if you're familiar with an old grandfather's clock, if you ever seen someone wind one of those old things, they have to, every night my grandpa would do that. He'd get there and he winds, he basically gets a bunch of counterbalance weights and raises them high up. And over the course of the day, those counterbalance fall. And as they do, they give back energy to the system that runs your clock. So we're always interested in a change in gravitational energy. That's equal to mg delta y. So that's one of our big equations right there. It looks small, but and it is. It's a good thing about it, man. It's using that a lot today, and I guess today that's when we're going to be using it. And remember, for the springs, we were able to have an analogy of this for the springs with the work done by a spring. So delta US, so this is the UG and it's the US. This is the elastic potential energy. Oh, I can't see your screen. Uh-oh. It says here my camera is on. You guys can't see that screen? That's a new one. According to the status bar, let me try. Oh, I can see it. Okay, so now Matt, it looks like it's maybe on your end. The status bar here says we are sending, and Kyler says he can see it. So anybody else out there? All right, thanks, Matt. All right, sorry about that. All right, so well, you haven't missed much. This my soothing voice here, and just outline the ones we covered at the very end of not yesterday's but Monday's lecture. Delta US equals, and I say US, U sub S, I should say, but I forget the submarine and the sub. A delta U sub S equals elastic potential energy 1/2 K. And the book likes to write it like this: F squared minus X initial squared. But remember, each of these X's here is really a delta X already relative to the equilibrium position, X naught. So this is how far the string, or how far initially the spring is stretched or compressed, and then it moves, and this is its final position after to the final resting position relative to X naught. So, and I guess another little thing, didn't spell it out because class was ending. But if you notice, when we derived this equation, we initially derived from the work done by the gravitational force, and it was negative mg delta y. And the energy from a spring is negative 1/2 K, this quantity here. So a nice other useful quantity to know is delta U for anything, any change in potential energy, be it a change in the gravitational potential energy, change in the spring potential energy, change in electrical potential energy. It's next semester. This equals the work done by an exterior or external force. I always want to say exterior, a house, but external force. And it equals negative the work done by a conservative force. I know I didn't really put that there. I was kind of ran against the barrier of time. And these equations for your potential energy always is working with a conservative force, which we talked about that on Monday. Yeah.
So the delta U as equation is like the equation that we saw with the work external equals positive K over 2.
Yeah. Mm-hmm. Usually we're talking about storing energy in a system, and well, we are always talking about storing energy we can use in a system. And to do that, you've got to do some work to get that energy stored. Sometimes it's not necessarily us. The hydroelectric dam, good old Mother Nature does that for us. She uses energy to evaporate water in the oceans or lakes, makes a cloud. And like today, it's like weather like today, it rains, and it rains high in the mountains. So that that mass has been transported to a higher elevation, the delta Y has gone higher, positive, and therefore we can store it behind a dam. We can make it, and then we can make it do work for us. But gravity's not doing that. Mother Nature's got to do that for us. And when it comes to the springs and stuff like that, it's probably us cocking a gun or having a machine do it for us. So what can we do with that? So just add all the other energy formulas we know. There isn't many left. There was, well, one, we've only known one up to this date before we entered Monday, and that's kinetic energy. Equals K equals 1/2 mv squared. And there's only one other type of energy we can deal with here so far, and it makes it more realistic. And this is the energy robbed by friction. We've talked about work done by friction, but now we can actually put that in the context of an energy equation. Kinetic energy. And you might think we write this as WF, a little f for W friction. That'd be a good guess, but the book likes to call it this, NC. And that stands for work done by non-conservative forces. Because up to this point, we've got only conservative forces, and then we had the kinetic energy equation. And work NC, actually, it's lowercase or uppercase? It's uppercase. Work done by non-conservative forces, and when I say it, it's always friction for us, all right? But the book's, it's trying to, I guess, to expand our horizon a little bit, because it doesn't have to be friction. It can just be actually a rubber band, which isn't perfectly elastic. That's a non-conservative force, technically. Wind resistance, another type of friction, that's also a non-conservative force. It can be just about anything. In the real world. It can be very complicated to figure out. For us, WNC is going to equal the work done by the frictional force. And we've had that for a week plus now. So it's going to be frictional force delta R, and we're going to make that positive actually. Mu Fn delta R. So we're going to keep it positive. Reason to follow. So anytime we have this term WNC, you can just, if it's given to you, that's great. If they say, hey, or maybe you're trying to find it. We've done that in a couple recent examples. What's the work done by the frictional force? What's the work done by the non-conservative force? Basically, you're trying to figure out how much energy you're losing to friction. So you solve for that. If you are given the frictional force, or if you're given a mu, coefficient of friction, then we can actually compute that term and add it into the big equation coming up right now.
Why is there no cosine theta in that?
Well, what would the angle be for a frictional force? The question is, why is there no cosine theta? What would the angle be?
Because it's always cosine 180.
So
So
you're,
then it'll just be a negative and two negatives on top.
well, it's the angle. If we actually, you might wonder, where's the angle at? And if this were the frictional work, definitely just the frictional work, I'd have to stick in that good old cosine 180, and it'd be a negative number. And it'd be that way all the time. But we're going to find out that the way the book, sorry, causing distress. Equation coming up anticipates WNC being less than 0. So it places it on opposite side of equation to make it positive. Okay, and so that's why it's keep it positive. You'll see that coming right up. It's the next big equation. Actually, it's the last big equation for this chapter. I said this chapter goes fast. So we're going to basically work with these equations from here on out in this chapter today. Back in the, I guess it's a good time for a little story here. Back in the mid 1800s, a guy found out mid 1800s, guy by the name of James Joule found out you could drop a mass and it would cause an increase in temperature of the liquid. How do you do that? Well, pretty simple apparatus, but why the guy didn't go crazy with this, I don't understand, because man, he took a lot of data. And when you drop something, you don't think, oh, it got hot. It did get hot. You just couldn't measure it. It's too small. So he had figured a way around that to where he'd be able to measure it. And here's these little apparatus. Get a mass sitting here, attached to a string, went around a couple pulleys, and it went into this device, which could be filled with liquid. And what's the string doing? The string causes a paddle wheel to move, actually specifically to turn. So this little paddle wheel in there. Paddle wheel that turns as mass falls. I just mentioned the concept of a grandfather's clock. I don't expect many people have one of those, but some in your family you do. You're at least familiar with the concept. You know there's big weights in there. And hopefully, yeah, I should say hopefully, maybe you are. Get a picture on YouTube, check it out. There's some big weights, and that's how it works. Now you put the weights up high, and the weights fall down, and the clock turns around. It goes around. So it's not. So if you think about that model, yeah, this will work. So as the mass drops, it's going to cause the paddle wheel to spin. And this was a liquid field device, which was that's insulated. Does anybody know what this device is called? You chemists out there use it a lot. I don't know if you can call it that at the time, but he came up with one of the first ones. Device where you can have a container of liquid and you can spin it around and it's insulated from the outside world. Starts with a C, ends in a meter. This guy's called a calorimeter. What he did was he had a thermometer in it. They'd have a little opening. Thermometer. So now we just had this equation. This weight starts up here at some y initial, and it's going to fall. Some y final. So initially it's up high, and it's got lots of potential energy. And as it goes down, it's going to lose that energy. At least that's what we have in the equation. Back then, he didn't know anything about those equations. But he found out that as it fell, it would cause the paddle wheel to move, and the stirring action would cause the temperature to rise inside the liquid. You might think when you stir your hot tea or your coffee, you're cooling it down, and you are, but actually you're putting energy into the system. How you're cooling it is you're mixing it up. And that allows the hotter material to become in contact with the cooler air, and therefore it cools it that way. But technically, what you're doing is you're actually putting energy into the system. You're causing it to heat up due to your stirring action. But the other action overwhelms that small little increase. When I was your age in physics class, actually, that was one of my test questions. One of 3 test questions Dr. Durbin gave us. You have coffee at 50.0 degrees Celsius. Calculate the final temperature of the coffee after reasonable stirring. You had to come up with all these devices. You had to come up with this shape of the when you stir it, and the surface area becomes this canonical shaped, and it was a bear of a problem. But it was fun. I still remember it to this day, obviously. So anyway, back to this. It falls down, stirs the material, and you see an increase in thermal energy and temperature. It's not a big increase, but nonetheless, he had a very good thermometer. So why did he come up with this? Does anybody know how he had the good thermometers? He came up with this. I don't know what motivated him to do this, as he had some of the best thermometers in the world at the time. So we'll do a history lesson here. See if I know what his business was. How would he have good thermometers? And he's not a real scientist. I don't know exactly where he makes the bridge, or he goes, turns the corner, becomes a scientist. I don't know if he actually does become technically a scientist, but his family business has good thermometers. And he gets to wondering about this. He builds this apparatus in a dark old room, and he sits there for months, I don't know, years, I don't know what he does, dropping the mass from different heights, filling it with different liquids. And every time he found out, if I double the height, the temperature increases, it goes up twice. If I make the height half as great, the temperature increase goes up by 1/2. So he found a correlation between potential energy, what we call, and the temperature increase in the liquid. As the potential energy decreased, that energy went into that liquid. So he's showing you energy is being conserved in that way. So what did his family business do? They were a bunch of brewers. They made beer. And so they had good thermometers. He found a loss of potential energy. Y final is smaller than Y initial. So by that equation we had before, that means there's going to be a loss of potential energy equals a gain in thermal energy. I guess I should say loss potential energy of M, mass M, equals a gain in thermal energy of liquid. And we'd call that temperature. That's how you'd measure it. Technically, it's thermal energy. So they collected all these data. He's British. I don't know if he's Scottish. I think he's Scottish, but don't quote me on that one. Anyway, he takes all these data and goes up to the Royal Academy of Sciences to present his information, his results. Because at the time, no one had even thought about this. They thought the mass would fall and that energy just goes away. It gets destroyed. And when you raise the mass up, energy is being created. Somehow it just came out of the air. I don't know how they exactly rationalized it. There's actually a whole slew of historical people trying to come up with this, but he's the guy who's going to cement it. And when he presented all his data, and he said he was a brewer, his family was a bunch of brewers, they laughed him off the stage. I don't know, but the British are pretty prompt people, so courteous people, I guess. So they may not laugh him off the stage, but they didn't take him seriously. He actually publishes his work in a Scottish journal. That's why I think he's Scottish. And it was an obscure Scottish journal. But what he publishes is that total energy of a system is conserved. And only can be shown via experiment, not theoretical. So there is no theoretical proof. I showed you how to derive those individual equations for here's the work done by the spring, here's the energy done by the gravitational potential energy change in that. But I can't show you that the total energy of a system is conserved. In other words, the energy you initially have equals the energy final. And but this is what he came up with. Put it in my terms. If I could measure the total, of course, total means all energy present in a system at a specific time and place, no matter the form, and when I mean the form, I mean these equations we just had. Maybe you got a spring in the system, it's got some energy. Maybe it's the spring is raising a mass, so you got some potential energy. Maybe it's moving, you got some kinetic energy. Maybe there's friction present. So that's, you can have this energy initially in the system be locked away in all these forms. We're going to call this E initial. We're going to quickly abbreviate that to EI. Then I would find at a later time say later time, the same system would have the same total energy. That's total. And we're going to call that, of course, E final, E sub F. Although it may be distributed differently. Get something. In the old days, we'd be doing this like a little lab, a little project we'd do, but we're not in the old days right now. So what I mean by all this, so here you got a system. It's a dart gun, you know, and look at me, I do some work on it. I cock it. Ooh, it looks cocked now. So I measure the energy. It's the energy in that spring. Okay, so I do that. I gotta pull up my elastic potential energy equation, which is the work in the spring equation we had last week. And I find out how much energy is stored in that spring, and that's my E initial. And I'm not going to shoot it. Well, I'm going to shoot it off, but I'm going to hold it down. If you fire the gun off, you know, now imagine this thing's coming out real, you know, not slowly, but imagine slow motion. You know, you got a slow motion camera. All the energy in the spring goes away. It's gone. The spring has no more energy. Where'd the energy go? This guy's got the energy, and it's in the form of what? Where's the energy? What form of energy is it in now? Kinetic, right? Energy of motion, right? And if the dart hits the ground, well, the dart stops moving. Where'd the energy go? Anybody out there in virtual world? An object hits the ground, stops rolling. Where'd all that energy go? What took it? What took it away? In the ground. In the ground via what? It does go into the ground. But what robbed it of energy? Where'd the energy get transferred into? What? Well, actually, as it falls down, it would go gravitational, but eventually it's going to come to a stop. So what stops it? I mean, how's an object come to a stop? There's going to be a force on it. Friction, yeah, friction. So the frictional force robs it. So if you can sit there and measure the energy, have an energy monitor. Initially, you got so much energy in the spring, and it's the number. Let's say it's 20. I don't know, 20 joules. Maybe too much for a spring. Let's just throw out a number, 20. You shoot the gun off. No more energy in the spring, but if you can measure the kinetic energy of that dart, it would be 20 joules. And as it falls down, it may pick up a little bit there due to the potential energy, but when it hits the ground, it comes to a stop. And if you figure out the work done by the frictional force to bring that to a stop, that's 20 joules of energy. And actually that would go into a frictional force. Is usually we know that manifests itself by a rise in temperature. We've all, or a lot of us have slid across that old basketball or volleyball court, diving for a ball, and you get that nice floor burn. Boy, you know your temperature goes up. That's frictional work right there. And the system rises in temperature. So all the while, the amount of energy, total energy is there, but it's been transferred from system or from piece to piece, you know, shared with another energy term, or maybe completely transferred from it. And this gives us the big guy, which looks small, but I'm going to expound upon it. Conservation of total energy. It's got to be total because, yeah, obviously the spring loses energy. It's gone. But if you account for the system is you don't allow any, you know, and now the dart has gone off with kinetic energy, it's still there in the system. Okay, so individual pieces can lose, but the total itself stays. This equation holds forever. If it doesn't hold, you're missing something. And this is what, even though James Joule didn't come up with this quite this elaborate, the only thing he could tell you was potential energy goes into thermal energy, and that was conserved. And as they started looking into it, and back to the conclusion of James Joule, obviously they took him seriously. Eventually, they named the unit of energy after the man. The Scottish Journal publishes his work. They accept his findings, even though it seems like it just was counterintuitive to people at the time. And that Scottish Journal, which I got to look it up. I know I had it a long time ago, and the name escapes me. They're still very proud, or they may be defunct now, but they were very proud that they scooped the Royal Academy of Sciences. And they had this watershed equation. This is one of the greatest watershed equations in physics we've ever had. This little bitty guy right here, conservation of total energy. Everything you do today relies on it. Even you chemists out there, you can count on a reaction always being the same. Due to energy conservation laws, that's possible. We physicists, we don't have a corner on it. Just we depend upon it as much as you guys. Definitely biology folks. Oh my gosh, trying to figure out how biological systems work and how you can survive. Talking energy conservation. Now, as far as energy goes, we can expand upon that relationship. So E initial equals E final. For us, that energy could be represented by the following terms. K initial, so how much energy when you start the clock off, or if you look at the system for the first time, what's moving? Everything moving in there has got kinetic energy. Gravitational potential energy. How high up is it? And the last one I didn't make or I didn't say anything, and then I got called out in the class. There could be gravitational potential energy. The dart is falling, so it starts off higher, and as it goes down lower, you can have an energy due to that. Plus, is there a spring present? So the spring can actually have energy in it. And you know, I mean, this dart gun, we started off my little story, I had it all the way cocked. There you go. Excellent example of energy conservation. And it does happen very quickly, but when I pull the trigger, the spring doesn't instantly lose its energy. It's very quick, but nonetheless, if I had a big enough, fast enough camera, or if the spring were actually long enough, I can actually see the spring starting to expand back to its equilibrium position. And when it does that, it's losing energy, but still got some, always losing some and getting smaller and smaller. And as it does, the dart goes faster and faster and faster. So if I start the clock somewhere in mid-stride state, so to speak, I have a kinetic energy term and a spring term. Okay, and if this thing's above the ground, it's going to fall, then I'd have a potential energy term. And if you look at those equations we had before, that's all we got. We just had a kinetic term, gravitational potential, and a spring term. And there could be a lot more in life. I put an old equation sheet online. So people have asked me for it. So I put one. They said, do you have an equation sheet from, previous? I said, yeah, from last year. Usually hand one out. So I put it online last night or this morning, what have you. And there's a few extra terms on there which we didn't get to. An object which rolls also has energy stored in it. It's called kinetic rotational energy. I mean, don't do it, but that's why we don't stick our hand in a fan blade. It's not moving like a dart. It's not sailing through the air. Hopefully your fan's not doing that. But it's rotating. We all know when it's rotating very fast, you do not stick your hand in a fan. It's got energy on it. It's going to hurt. All right, so these are the only terms we've got. On the right side, we have exactly the same possible terms, but we just put the little F subscript for them. How fast is the dart moving or the object moving when we consider the final conditions? And the final usually is the area we're interested in, or maybe the initial. We're going to work backwards. How high off the floor is it compared to the initial? Did it drop in potential energy, or did it increase? And finally, what's the spring doing if there's springs even present? Is the spring compressed more, or is it compressed less, or stretched more, or stretched less? And finally, over here's where all our energy is initially, but on the right side, we got these three terms and another guy which can rob us of energy. So that's why he's always stuck over here. And this is the work from the non-conservative force, that's your friction. And that's why he's positive, why we make it positive. We know where he goes. He will always be on the right side. He will always rob you of energy. Here's how much energy you have initially. Think of like money. I got $100 and it's split up among, these three terms. And we're going to go through a day and you're going to go buy some stuff at a store. You're going to, you're going to find some loose change on the ground or something like that. So your amount will change. But what's also going to happen is you go through the day and you make some purchases. You're going to have to pay your taxes. That always takes away money. So your income over here will get split up among these guys, and definitely the frictional guy, the taxes will take it away from you, okay? We never see this guy on the left side. So he's always on the right side. He's always, energy is going to go into him. We're not going to be able to get it back out. So that's why he's always positive. We know he goes here. He can't be over here. We're grateful he's not. The world would be horrible. But the frictional force can never be positive over here, because that would mean the more friction you had, the more initial energy you got. Now as you move something across the floor, what have you, and rub it, there's frictional force, and it takes it away from you. We can write all these guys out if you'd like. 1/2 mv initial squared plus mg y initial plus 1/2 k delta x initial squared equals, same equations, just put the subscripts become f instead of I. And finally, the WNC, well, we've already written that on the previous a couple pages before. It's either equal to, I'm going to put it up here as a bracket. You can either see it as maybe WNC, you're solving for it, or maybe you're given enough information to actually figure it out. Or UFN delta R. So this is the three ways you can write WNC. Okay. This is the big guy. Oh, heck, circle the whole gosh dang thing. That's conservation of energy. Okay. If friction can be ignored, so then we have just K initial plus UG initial plus U spring initial equals K final plus UG final plus US final. And this is called initial mechanical energy. And this is your final mechanical energy. And if you throughout, I know I was throughout the terms, at least a few of the class, hopefully all of them. I mentioned when we did the what's going to be covered in chapter 8, conservation of mechanical energy. Me, it's just like, okay, it's conservation of energy without friction. And so, but that's what it is actually. But it's to me, it seems a redundant step. It's just why have it? But the book's got it. And so if you're reading in the book or your next problem, they say, oh, mechanics, they mention mechanical energy. This problem's, mechanical energy is conserved in this problem. That just means there's no friction. And you can do the conservation energy equation without that term there. Okay, so that's what I mean. We're technically, we are done now with chapter 8. That's it. But here's some concerns. Concerns or pitfalls. One, all delta x's, remember are stretches or compressions from x naught. All right. For our equation, the spring was horizontal, delta x, but it could be vertical. And that just means we have delta y. So no big deal. We've done, I know that worksheet we had, I know one class did it, or maybe a couple of classes had the problems, and the problems are all online now. So if you from Monday's talk, when we split up the problems that the classes did, the video is yet to be posted. It should be done. It had to be compiled last night, but anyway, it should be done, ready to go. It's got to put in the right spot. But the PDFs and the scanned in solutions of all those problems are available. Hopefully, fingers crossed, it should be available on Canvas. Okay, so if you want to see, I know we had some vertical springs there. 3. This is the conservation energy equation for all possible, possibilities for your what could be present, but that doesn't mean they're actually there. Not all terms need to be present in the conservation energy equation for a specific problem. What I mean by that is for a problem, if no springs are present, then you do not have the initial spring potential energy, or let's put that in there, the final one. So I see this every year. I guess they missed the class. They see this big old equation, and then they think, oh, that means there's a spring. Yeah, this is where you put the term if there is a spring. If the object isn't moving, there's no kinetic energy. If it's not moving initially, the Ki is initial, or, just zero. If it's not moving at the end, K final is zero. If it's never moving, we could talk about taking a spring and stretching it out. So its initial conditions, I don't have my spring with me. My initial conditions would be an initial stretch, and I stretched it out to a final stretch. Yes, it did. It moved in between there, but when I have my initial, the mass was always still, so there'd be no kinetic energy term. If the object doesn't raise in height, and of course you can't do it too easily here, but raise in height up and down, there's no change in potential energy, gravitational potential energy. So that term would be zero. Or if you want to, you say, well, it starts on a tabletop at a certain height above the floor. It ends up on the same tabletop, same height. So these two terms would be the same. They cancel out. So just be careful about that. I get people that's always trying to put stuff in here. You can have more than one spring. You can have, we can have, just like we did that in the worksheet, we had a couple springs and a couple of examples. So this represents the spring energy, but if you got two springs, you got two terms for this, because you may have two different Ks, maybe two different stretches or compression. All right, so this is just a generic equation for the conservation of energy equation, but you have to modify it for your conditions. Okay, these are the terms that can only be present though. Let's see one of you guys in action. A 0.200 kilogram mass sets on a frictionless, let's start off with friction, horizontal air track. Connected to a spring, and the spring is characterized by a spring constant of 5.00 Newton per meter. A person pulls on the mass and stretches the spring .100 meters and releases it from rest. And the spring's going to cause the mass to move back towards its equilibrium position. And because it's x naught. We'd like to find the speed. Let's find the speed Vx when your spring is stretched 0.08 meters. Of course, that's from equilibrium. Whew, all right in there. Okay, so I like to draw a little picture to help me out on these guys, on these kind of problems. You want to be able to identify. We're going to use conservation of energy. I mean, you probably don't have to, but you'd find work, and sometimes it's just a mess to use these other equations. But here, the conservation of energy usually it gives us a way to do it fast without using vectors, which is really cool. So this is going to be initial. This is your E initial stuff. So we have to account, if we're going to actually use this equation, you've got to figure out, if you know, it's possible to use it at a given time. Do you know the kinetic energy, the initial gravitational energy, and the initial spring energy of a system? Okay. Okay, so there's our hand initially, mass. So this is initial. Let's see, let's call this guy here X naught. So we can call so initially when we stretch it back 0.100 meters, and V initial equals 0. It says at release, releasing it from rest. And this is on a tabletop. This is air track. It's on air track. My bad. Doesn't look like too much like an air track, but you know, I figure it's off the floor some way. So let's call this Y initial. And this is the height of the table. I guess I should say height of the air track. And it's above something, and let's call it above the floor. How high up do you think a table is? Anybody? How high is the table off the floor? 3.5 feet? Okay, let's call it 1 meter then. stick with the metric system. So let's call it 1 meter. That's okay. It's okay. It's okay. All right. So here's that's what the initial. Remember, as soon at the moment we release this spring, the hand has just left the mass. This is how far it's stretched. That's how much energy is in the spring. The kinetic energy is 0 because I didn't initially give it a push or a shove. I just let go of it. So I'm just let go of this thing. So initial kinetic energy is 0. And it might have gravitational potential energy. That would be the mg y initial term. Final. E final. X naught again. So the object is moving back towards equilibrium. The spring is snapping it back. And X final equals 0.08. I call that a delta X up there. So maybe I should keep these as delta X's. It's to hit home just a little bit that these are measured relative to, remember, X naught. And the object went from here to here, so there's a good chance, and we think about what spring's doing, it's moving. E final equals I don't know. I don't mean this to be a negative sign. I just mean this to be arrow on red. So see what I'm drawing at. That's the height of the table. What's the final height of the air tracker table? Same as initial, right? Same as initial. So how's the gravitational potential energy at this spot, gravitational potential energy of the mass, relate to the gravitational potential energy of the mass down here after it's moved a little bit to the left? I see how it's going to be related. Right, it's not going to change. That really hurts a lot of folks. They say, well, it's on a tabletop. It's got gravitational energy. You're absolutely right, it does. But the key thing is when we do these equations, we want to know how much it changes. You're comparing how much things change from the initial to the final. Now, total, it won't change at all, but some things will gain, some things will lose at the expense of others. And even though you, I'm 1 meter above the ground, I've got potential energy. You're right, you do. You get the same amount of potential energy at the end. So these two terms cancel out. That gets a lot of people. I used to set it on the floor, and well, you can't set that on the floor. You know, if some things are above on the tabletop, the problems will happen when they think they see that tabletop. They it must have gravitational potential energy, and it does, but it just doesn't change. Even the floor is just, it's always, gravitational potential energy is always measured relative to something. You can measure it relative to the floor, you can measure it relative to the basement. You could say the center of the earth, but at that point, you know, the G is changed dramatically, so you really can't do that. But it's nonetheless, it's just wherever you want to measure it relative to, and whatever you measure it relative to, we don't see a change from here. All right, so we got our initials, and we got our final, and we want to find out the final right there. So then we just run back to our conservation of energy equation. If you want to write up all the formulas first, but I go right ahead. And of course, it doesn't matter the order of these things. And hopefully, I get in the same order. That's not necessary, obviously. Just adding. Doesn't matter the order of operations. So there you go. So what do we got present? And what's not there? Well, initially, like I said, I wouldn't write all these terms out. Maybe when you get used to them, if you want to, it's fine. But after a while, you get used to them. Just keep the abbreviations. It's like figuring out a work done by the normal force. It was always, Fn, delta R, cosine, theta. But before I'd figure out, go to all my trouble to figure out the normal force, I'd sit there and get those angles first, because when you hit cosine 90, that term just drops away. It says it's frictionless. This guy's 0. No friction. Yay for us. This guy's 0. Why? The initial equals 0, so it's gone. And we definitely have the spring stretch from equilibrium, and the final one is not stretched as much, sorry, not stretched as much, but it is there. The object is starting to move. And these guys right here, these gravitational potential energy terms, UGI would just equal mg y initial equals mg 1 meter. UG final equals mg y final equals mg 1 meter. And so UG initial minus UG final, whichever way you like to solve it, just equals 0. So these two terms right here are just gone. And so you shouldn't worry about them either. I went through and gave you a unit value for how high the table is, but it said you were moving horizontally. If you're moving horizontally, you're not changing your y position, so those terms drop away. If object moves only horizontally or ends up at same height it started, delta y, so I suspect this mg delta y equals 0. In that case, you don't worry about UG initial or UG final. Okay, so what terms we have left standing after all that explanation? All the energy was in the spring. It goes in the kinetic, and some more is left in the spring. So initially it starts all in the spring, and then it's going to start sharing the energy. The object, the mass is going to start moving. It's going to gain kinetic energy at the expense of the spring, and that's why the spring isn't stretched as much anymore. Now is when I'd write those equations in there. Okay, so I look up what's the equation for my spring. Oh, it's 1/2 K delta X initial squared equals the kinetic energy equation 1/2 mv final squared plus 1/2 K delta X final squared. Let's see, I know the K's. I know my initial stretch of my spring. I know my final. I know the mass. Therefore, I should be able to solve for V. For one thing, the halves cancel out. You can do that if you want to mathematically. Beware. People go slap happy with cancellations. 1/2s cancel, but not K's or the M's. And that's because there's a 1/2 in every term here. So you can divide by 1/2 here, it goes away. Divide by 1/2, it goes away. Divide by 1/2, it goes away. I'm going to divide by K. Great, it's gone. I'm going to divide this term by K. Great, it's gone. You divide this term by K, it's still there. It's M over K now. Well, MV squared over K. You still got the 2, it's also still there. Likewise, you divide by the mass, sure, you can eliminate from this term, but it's going to be in the denominator on these 2 terms. So be careful when you start canceling things out. You got to, if they cancel mathematically, it means it's in every term. It doesn't have to be, but you still got them present, so they don't just disappear. We get 1/2, what is it, 5? 5. 5, that's our K, times our initial stretch of 0.1 squared equals 1/2 times, where's my mass at? That's 0.2 kilograms times V final square, which is what we want, plus 1/2 times 5 is 0.08 squared. If you have a calculator, you solve for V final. Times 0.1 squared minus 5. I get 0.3. That means yes. Great. So, you be careful with your algebra here. You can do intermediate steps if you're not used to punching a lot of numbers. You know, times like I do, you shortcuts. You know where you can combine things easier at. So that's it. All right. That little. I mean, we did deal with the spring equation, but you have to worry. Oh, is it negative? Do I use a negative equation? Do I use the fine or the positive one? I don't know. Which am I worried about? And just if it were used to Hooke's law, that's actually a vector force. You have to figure out, oh, I can get my acceleration. Yeah, go for you. Good for you, but it's non-constant. It's not a very constant acceleration, so you can't use the equation of motion. So you were actually be in a pickle there. Yeah, actually, you couldn't do this without invoking integration. You couldn't like figure out the acceleration of the object using Hooke's law and then plugging in an equation of motion because acceleration is not constant. So this is actually the only way you could solve this problem, easily at least, without doing a lot of stuff. Let's do another one. These are fun. Oh, sorry. Any question on that? I guess just ask any questions about that. I mean, it's nothing. Okay, I'll do another one. Let's put friction in this guy. A 3 kilogram crate slides down a ramp that is 1 meter long and inclined at 30 degrees. So you get this mass, this 3 kilogram crate. Actually, it wouldn't be a big crate, like 6-7 pounds. But anyway, it's a good size, I guess. You put this little box at the top of a ramp, and you let go of it. If it starts from rest, and experiences a constant frictional force of 5 newtons, find the crate speed at the bottom of the ramp. Okay. Make it really big here. So we know the mass, 3 kilograms. This is initial. So we have to know what's going on up here as far as spring energy, gravitational potential energy, and kinetic energy. We have to be able to account for those 3 terms, and only those 3 terms. Like I said, there might be more. Maybe there's 2 springs or something like that. Then you got 2 springs. But you got to be able to account for all your potential energies, both gravitational and spring, and how fast the object's moving. And down here we get the final. So we'd like to find out, as in the previous example, we'd like to figure out the speed of the object at the bottom. So it's got something to do with the kinetic energy, but we also got to once again account for how much energy is in the springs, how much energy is in gravitational potential energy, and if there's friction present, how much energy is it raw from the system. We know it's present because we say so. Delta R is 1 meter. And we know this guy's at 3 degrees. For one thing, in this case, is there a change in gravitational potential energy? Gravitational potential energy, will this thing see a change in Y? Yes, it does. It's sliding down around, right? So we have to figure out what our Y initial is, and it's not given to us. Oh, how are we going to do that? So, if we call this 0 down here, so this whole baseline here is 0, that's where our little object's going to wind up. Then how high is Y final or Y initial above Y final? Well, we have a little triangle here, and we want this side, and we know this angle, and we know the hypotenuse. So Y initial over 1 meter equals sine 30 degrees. Y initial equals 1 meter times sine 30 degrees. And really, when I say Y initial, it's really Y initial minus Y final. It's relative to Y final. So every time we measure a Y, we have to measure it relative to the baseline. And generally, we make either the initial or the final 0, one of the two. In this case, we start off high, so we're going to make the final one 0. Okay, now we know we can do this before. We can go back to good old Newton's second law. It'd be a bear. We'd have to rotate coordinate systems. We'd figure out the acceleration of it down the ramp by summing all the forces along the ramp. And then we'd have to, since everything is constant, the frictional force is constant, everything else is constant, then we'd go back and we're legally able to use the equation of motion. And we know that V naught is 0, and we want to find V final along the ramp. We call it V final X, and life would be great. That'd be it. We could do that, and it would be a bad way to spend a November day, but maybe we can do it a different way. Let's look at due to energy conservation. So just think what that would look like. Think of, you're using Newton's second law. You got to do the sum of the force in the X direction, sum of the force in the Y direction. You got to figure out your forces. You got to break them into components. It's getting messy. You're getting a normal force. Actually, you won't need a normal force here because you're given the frictional force, but it makes it a little bit easier. But nonetheless, there's a lot of stuff there. And once you get the acceleration, then you got to go to the equation of motion. So it's multiple steps here, multiple sections. All kinds of places you can make a little bit of a problem, especially consider these are all vector quantities. But we can use E initial equals E final. Okay. Okay, initial plus U spring initial plus UG initial. I think I swapped my springs and the gravitation, like no big deal. All right. Generically, that's what it is. And if you don't have to write this, if you're familiar with it, or if you just look at it, you know, why I don't have to write all these. I'll just knock them off as I see, as I look at the equation or see, look at my problem. But let's just do it for the folks who are gonna, you know, hasn't had this and gonna look at the video later. What is their initial, or is there initial kinetic energy of the mass? Up here at the very top. Is the mass moving? In other words, is the mass moving? Yay or nay? Anybody out there in the virtual world? Is the mass initially moving? Who's out there? Who's out there? Thank you, Kyler. No, it's not. If it's not moving, that guy's 0. And that's because V initial equals 0. How about the spring? How much is the spring compressed or stretched? There is no spring. There you go. 0. No spring. I shouldn't laugh. It's I'll give the exam. People, got to be a spring. You wrote that up here. It's got to be. I've got to write this because, as you see, each problem's energy conservation, but each problem's got unique terms which are present. Some of them got all the terms present. Some got very few. This is better be non-zero because if it's not, then we have no energy in the system. But yes, it starts off high. So this guy here is present. So we're leaving. Kinetic final. Yep, it's there. It's moving. Just think the object is sliding down a ramp. It's got to be in motion. It's going to eventually hit something, but at the bottom of the ramp, it's still moving. The final spring, there's no spring still. No spring still, so it's not even there. Gravitational potential energy, well, we'll keep him there, but it's if you want to, this guy's going to be a 0 term because we're going to put in good old Y final 0 and that goes away. But we should get ahead of ourselves in this. And is there friction present? Yes, there is. So we want to keep that term. So we're only left with this. UG initial equals K final plus UG final, even though that guy's going to drop away here pretty fast, plus the work done by non-conservative forces, aka friction. So what we have, mg y initial equals 1/2 mv final squared plus mg y final, plus the work by the non-conservative forces of friction. That's not given, but what is given is the frictional force. Oh, that's lovely. I had to figure out that Fn. No mu is given. I was told the frictional force. This is mu Fn. All right, it's already been given to you. So you go back, like I said, there's multiple ways you can write that equation. Where is it? Good heavens. There it is. So I'm given the frictional force on how far it travels. I'm going to use this term right here. If I was given a mu, I'd have to figure out my normal force. That actually entails a little bit of a force table. Then I plug in the mu and I take the delta R. I'd really like them for me to tell me how much work or how much energy was just robbed from the system, but oh well, they didn't quite give me that. So this is going to be the frictional force times delta R. So what are we solving for? We're solving for V final. So let's get V final kind of all by himself. You can't divide by mass. You could, but you're still going to be stuck with him because it will be in this term here. It won't cancel out completely. So 1/2 mv final squared equals mg y initial minus mg y final minus the frictional force delta R. V final is going to equal mg, let's do y initial minus y final. A few terms out here. Minus the frictional force, delta R. I divide by m. I multiply the whole shebang by 2. And take the square root of it. It should work out now, hopefully. V final equals 2 times my mass of somewhere 3 kilograms times 9.8, that 9.8 positive. Y initial was 1 times sine 30 minus 0 minus my frictional force of 5 times how far the frictional force acted, and that is the frictional forces acting along the ramp. So it's 1 meter. I wrote it nicely with 1 R, so it kind of stick out. I divide this by my mass, 3. So let's do it. 30 times 9.8 times 6. 5, 3. Get, oops, got a 0 there. What did I plug in there? Fine. Yeah, oops. My parentheses there. Forgot one of the parentheses there. Ta-da! That's a whole lot easier than doing the Newton's second law. Okay. There's a worksheet available online. We'll do what we did on Monday. We'll run a couple of those things through on Friday, start the class off, see how good you are with connect or the conservation of energy concepts. And then we will run in to do chapter 9. It's momentum. It's long once again. So I don't think I'll get all the way through it, but I can definitely get the conservation.